Mm. Maybe I lost it on Zoom. Yeah. It work on Zoom?
Welcome everyone to Fundamental Seminar at CMSA. We'll be delighted to have Meng Cheng. He'll be speaking about symmetry and many-body topology in mixed states. Please welcome.
Thank you. Thank you. Okay. First, let me double check. So, am I audible on Zoom?
Yes.
Yes. Okay, great. Thanks, Juven, for inviting me. It's always a great pleasure to be in CMSA. So I'm going to talk about symmetry and many-body topology in mixed state. This is the work mostly contained in this paper, building on previous work by Chen and Chong. Okay. And as time permits, I'll discuss some unpublished results with Tyler Edison. So, okay, so first let me acknowledge my collaborators. I have a really wonderful set of collaborators from whom I learned a lot about this subject. So Jen, this is done with collaboration with Jen in Penn State. Tyler, who's now a postdoc at Yale, and he's on the faculty job market this year. Chen has moved from parameter to Chicago, and Chong, I'm sure everyone knows him, and Jianhao, who's a postdoc in Penn State. All right, so this is going to be about topological phase of matter. So I guess I have an obligated slide on what this stuff means, even though it's probably not necessary for this audience. But in any case, let me just define what I mean. So we always have in the back of our mind some sort of Hamiltonian on lattice with local interactions and with okay, this is the usual setting for me to talk about topological phase, is that you have a local Hamiltonian with a fully gapped spectrum. So we have a gapped Hamiltonian, and we can define phases in terms of equivalence, adiabatic equivalence between Hamiltonians, meaning two Hamiltonians are equivalent if we can find a gapped path to interpolate between the two Hamiltonians. And we'll consider anything that's adiabatically connected to a tensor product state as a trivial state. Okay. And this problem can be enriched by demanding a microscopic symmetry. So the Hamiltonian should respect that symmetry. For example, the ground state should not spontaneously break that symmetry. Okay. And then we have a kind of symmetry enriched or symmetry protected problem. Now, throughout this talk, G will be ordinary, zero form on-site symmetry. Okay, for most of the talk, if not otherwise specified. Okay, so this is not sure this is like a common name, but I think it's fair to call this subject quantum many-body topology. So basically, we are interested in the global structure or the topology of the space of all the gap Hamiltonians. So try to sort out the structure of this space, which is a really wild space. And by topology, I mean the kind of questions you can ask. Oops. The kind of questions we ask are like, what are the connected components of this space? And by that, we just basically mean the different phases. Okay. And you can ask more refined questions like, what are the non-contractile loops in this space? And these are the pumps and even higher structures. So this has been a very active subject. And let me also give a definition of two terminologies which will be used a lot. This has been very common in literature. So there are these short-range entangled phase, which are basically phases without anyons in some generalized sense. And more precisely, we can define them as gap Hamiltonians with a unique ground state on any at least closed manifold without boundary. And there are also long-range entangled states. Basically, anything that's not short-range entangled, then they are long-range entangled. And they are typically, they are Hamiltonians with topologically degenerate ground states, and they will have non-trivial excitations like anyons. All right, so all of this are discussed in the setup of a ground state of gap Hamiltonians. Okay. And we have now understood a lot about them. So it's time to think about a more general set of quantum states, which are mixed states. Okay. So I'll very briefly discuss what mixed state phases are. This is obviously an ongoing effort to understand what phases mean and what possibilities there are in the world of mixed state. So I just want to use this as a kind of the invitation. Okay, all right. So we know in quantum mechanics we have pure state and mixed states, and in general you have mixed state because whatever system we are studying, it's unavoidably coupled to the environment. If you trace out the environment, then the system is in a mixed state. So it's common, it's ubiquitous. And here are a few examples of mixed states, which we encounter quite often. So obviously the most familiar ones are the Gibbs states, the thermal states, Hamiltonian at finite temperature. And more recently, the other mixed states, at least to me, the other get to appreciate that there are other kinds of mixed states. For example, you can have a quantum state just subject to some decoherence or noise. And they arise in noisy quantum simulators, which is, as everyone knows, is a very popular, is very fashionable these days. And you can also consider dissipative evolution of a quantum system, for example, governed by a Lindbladian equation, and for example, ask what's a steady state of the dissipative evolution. Okay. These are just some common place where we see mixed states. All right. I just want to mention that there's a very similar setup, which is systems with quenched disorder. And with quenched disorder, we also think about it as ensemble of ground states of a Hamiltonian. So many of the things that I'm going to say apply to this setup as well, even though they have important differences. And I forget to mention, so please feel free to stop me with any questions or comments. I guess someone will watch the Zoom chat. So I might not be able to keep track of it. All right, so this has a question of understanding mixed state quantum phases has received quite a lot of attention recently. So here is just a sample of recent papers that study aspects of this problem. Okay, so this is obviously a very a big it's obviously a big subject. So I'm going to discuss one small part of it, which we have some understanding. Okay? And this is the problem of basically generalizing the notion of symmetry-protected topological phase to mixed states. Okay. Now, this is probably the first example of SPT, the spin-1 Haldane chain. Again, this is familiar to everyone. The spin-1 Heisenberg chain with a unique ground state without edge, and if you have edge, you have these spin-1 half edge states. Okay? And these edge states are protected by symmetry, that the whole face is protected by spin rotation symmetry. And this is an example of a symmetry-protected topological face. So in this talk, SPT stands for symmetric short-range entangled faces. So the some short-range entangled states preserving a global symmetry. Okay. I've mentioned this characterization of SRE states before. It's a unique ground state on any closed manifold, no topologically non-trivial excitations. And we know, by now we understand that these SPT faces in ground states, they are characterized by responses, topological responses to background gauge fields. Okay? And there's a fairly well understood, even though not rigorously proven yet, classification of these faces, what are the possibilities, at least in all physical dimensions. Okay. All right. I'm not going to discuss this classification in great detail, but I do want to just review a couple of important ingredients which will be taken further, which will be applied in the setting of in the setup of mixed states. So to understand these faces, well, I said it's characterized by coupling to background gauge fields, but more practically, this is what one can do. So I'll focus on one dimension since it has all the features, it illustrates all the features that I like to consider. And similar things can work in higher dimensions, but one dimension is enough to discuss this. Okay, so I'd like to talk about this notion of symmetry localization. Okay, so suppose psi is a symmetric short-range entangled state. So a short-range entangled state that preserves the symmetry. Okay? Because it's short-range entangled, it cannot have spontaneous symmetry breaking. All right. So the state lives in one dimension, so it's some one-dimensional chain. And now we consider an interval, a part of the one-dimensional chain between 2 points, x1 and x2. And I'll call this interval gamma. So gamma just refers to this interval. Okay. So I have a global symmetry G, and take some element little g, and I've assumed that this is an on-side symmetry. It's just product of unitaries of different sides on this chain. So I can truncate this unitary to some region gamma, to this region gamma, basically in the obvious way. Just include all the sides in the region and define the truncated operator. Okay. Now, one can argue that so basically by applying this truncated unitary to this chain, we create a pair of defects at the two endpoints. And the reason that it just creates a pair of defects at endpoints because we've assumed that the state is symmetric. So away from the two endpoints, suppose we are in the middle of the chain, then it just looks as if we are applying the symmetry to the whole state. It doesn't really know what happens far away. So inside this interval, nothing should happen, and the only change takes place on the two endpoints, at the two endpoints. And now, for symmetric state, these defects, they can be healed by applying some local unitaries. Okay. So this is a statement that if you apply U of gamma, the truncated symmetry operator, to a symmetric state, symmetric short-range entangled state, then the effect is the same as applying some local unitary at the two endpoints. Okay. I think there's a typo here. This is V1 and V2, the two endpoints, 1 and 2. So we can, because the boundary of this region just 2 points, I can write it as V1 times V2. Okay. If we just must manipulate the equation a little bit, it means we have this kind of string order string order, that is U gamma combined with V1 inverse and V2 inverse has a constant expectation value, regardless of how long this interval is. So this is a string order in Haldane chain, for example. And so far, it has nothing to do with SPT, right? Or whether it's non-trivial or trivial, this is just a property of a symmetric short-range entangled state. Okay, all right. So now the claim is that whenever we can do this, whenever we have the ability to terminate this truncated symmetry operator on some local unitary, and then we can basically use this to derive, a way to characterize these faces. We derive some invariants, topological invariants that characterize the face, okay, how the symmetry kind of acts in the state. And this will, in 1D, this leads to the famous cohomology group cohomology classification in terms of HF2. So let me just flesh out how this is done. I mean, yeah, sure.
So since you want having the symmetry localized at the end of the strings, right?
Right.
So what's the importance of this string operator in the middle?
I mean, it's a symmetry, right? So these two unitaries, they don't actually act trivially on ground state without the string in the middle. It's only the whole thing that has a long range order in some sense in the ground state. So if you take a different group element, you have a different local unitary.
So string operator inside let's say this is 1 plus 1D,
right?
1D string inside the interval of the string commune with Hamiltonian.
Yeah.
But the endpoint of the original string somehow is not quite the commune, but you fix that by additional declaration of the point operators at the end.
Right. I can fix the excitation created on ground state by including some additional unitary operator.
Yeah.
It doesn't mean that I can make it commute with Hamiltonian. That's not generally the case, but I can annihilate the excitations created by the string.
So the string operator as a whole thing may not commute with Hamiltonian.
Well, so without the local unitary, yes. So this string operator may not commute with Hamiltonian. We don't need it to commute with Hamiltonian. We just need it to kind of act on ground state and preserve the ground state.
Okay.
Up to some exponential small corrections. Yeah, that's all I need. Right. Okay. All right. So from here we can basically derive the cohomology classification. This is acting like these V1, V2 they kind of serve as a kind of agent for the edge, right? We can do this without actually having an edge of system, just by looking at the truncated symmetry operator. So you have V1, V2, then these are, by definition, the symmetry transformations will have to satisfy group algebra. U of G times U of H is U of GH. But then this condition translates into V1 and V2 satisfying the group law up to some phase, since they appear in the product. And then this phase will satisfy some condition which can be derived from the associativity of these operators, and we get the cocycle condition, etc. So from this.
Sorry, I gotta maybe just clarify. I need to get clarified again. So on a closed chain, let's say.
Yeah.
The strings will commute with Hamiltonian because the string is built from the symmetry operator. Right?
On the closed chain, the string is just the symmetry itself.
That's right.
Right. Only when you truncate it, when you open it up.
When you say the string operator may not commute with Hamiltonian.
On open chain, so if I truncate the string operator, if I truncate the symmetry operator, and then I attach the local unitary to make it at least act trivially on ground state. But then it's not guaranteed that this string operator defined this way commutes with whole Hamiltonian. That's too much to ask for. Right.
But what's the choice of the endpoint here?
V1, V2 is just one choice. We just need to have one choice, and that's enough.
Are you able to classify these string operators in some way?
Well, this is trying to classify these endpoint operators. So in the middle, it's fixed by the symmetry, right? So the question is what these endpoints are. Okay, so basically we go through this familiar algebra Then usually this is done on the edge, but the truncated symmetry operators serve the same purpose, and we can basically derive the famous H of 2 classification of 1 plus 1 DSPT. And this can be generalized to higher dimensions and will lead to a similar classification. All right. Any other questions about this? Well, let me now illustrate it in a setup, in a simple example of a cluster state. So, all right, this is a model. I guess this is now a familiar model for most people. So we have just a spin chain of Ising spins or qubits, if you like. And I'll call the Pauli operator Z and X. Okay. So I've used different colors for the two sublattices, the blue one and the red one. And the reason being, I want to define all the product of X on the red side as one symmetry, the red X, the product on the blue side as the blue X. Okay, so we have Z2 cross Z2 symmetry, the spin flips on two sublattices. Hamiltonian just a translation invariant sum over Z x Z, okay, over the entire system. And they commute. This is a Pauli, all of them are Pauli operators. They commute with each other, they all square to 1. So the ground state is just given by having all of these operators being 1. Okay, so in this setup, we can very easily verify the localization property, the symmetry localization property. So take this one-dimensional chain and fix an interval between side 2m and 2n. And then let's consider the product of the red X in this interval. By the condition that Zx Z equals 1, we can easily see that this product of X is actually equal to Z right outside this one and Z right outside this one when acting on ground state. So this holds in the ground state. Okay. And then so we can define the string operator, basically a string of the red X decorated by the two blue Z at the two endpoints. This is the long-range string order in the sense that the expectation value of this O operator is 1, no matter how far away these 2 points are. So in the cluster state, well, it doesn't have to be 1, it approaches some constant. In the cluster state, this is exactly 1. And in anything that's adiabatically connected to a cluster state, this string operator has long-range order. All right, so there's a more like heuristic or intuitive picture to kind of visualize this string order or the symmetry localization. That is this decorated domain wall picture, or decorated defects, maybe more precisely, since domain wall is something that you discuss in symmetry breaking state. So, so you write a wave function in the eigenbasis of red X and blue Z. So the red X eigenbasis will be denoted by plus minus the eigenvalues, and the blue Z will be up and down. We can just basically write down wave function and has these up and down blue spins, and then the red sides in between have plus or minus. And we know from the Hamiltonian that they have to follow a certain pattern. Any red side between two blue sides with the same spin has to have a plus charge. Any red side between two blue spins with opposite up and down spin have to have a minus. So the minus charge only appear on the domain wall of the blue spin. Okay, so that's a decorated domain wall picture. In the ground state, we have only such combinations of domain wall states, decorated by the blue domain wall states, decorated by the red charges. Okay, so this is what I just said. One of the two terms, which is red X with 2Z, blue Z, make sure that this pattern holds in every state in the ground state, in this expansion of ground state, and the other term in the Hamiltonian kind of proliferates these domain walls and make sure that they are superposed in the ground state. All right, and again, this is a very general pattern for symmetry-protected topological phase, or SPT, is that we can always think of them as some sort of decorated defect states. If you actually break the symmetry, you will have decorated domain wall states. And each one of them is fully gapped, right? So if you look at one of them, well, here it's even a product state. In higher dimensions, each one of them should be gapped because we want to superpose all of them. So we better have gap states to begin with. So for each defect state, for each configuration of defect, there shouldn't be any gapless modes anywhere. And we want to superpose them in the ground state, and in the superposition allow for all kinds of different configuration of defects. So if we deform the defects a little bit locally, that should not change the charge of, for example, rest symmetry. Okay? So to make sure that all the states which go into a superposition have the same charge, otherwise the symmetry would be broken. And then there's a last point, which is a little bit more subtle, that is when we move around in a space of defects, when we continuously deform these defects, there shouldn't be any barrier phase when we deform them. When you go around in a space of possible defects, there shouldn't be any phase. Otherwise, that's an obstruction to form a coherent superposition of defect states. All right, so all of this have been fairly well understood in the context of ground states. The three sentences I just said in words, they can be turned into a precise mathematical formulation of what these defect declarations are like and what kind of rules they have to obey. Okay. So now I want to actually turn into mixed states. So far everything, this is like a review of what we understood, what we have understood about the ground state SPT phases. All right, any other questions?
So what you was asking, is there a classification of these type of string operator? So is that classified by just the Tuchel cycle you write down here?
Yes, we just classify Tuchel cycle. Another way to, sorry, let me. In this Z2 cross Z2 case, basically it's classified by looking at the charge of the, say, the red Z2 under the blue Z2 symmetry, the endpoint. But that's a well-defined quantum number. You cannot have different charges, otherwise you would have symmetry breaking. Okay.
So is there, what's the relation between the classification of the one part of the SPT and the classification of the string operator?
I mean, this, as far as I understand, it's derived from, so we first have this characterization of states in terms of string operator, string order, and then from there we derive a classification. You can also match it with a field theory classification, for example.
Just one-to-one correspondence.
I mean, it's the same, right?
It's the same, both are H2.
Yeah.
Okay.
Of course, before that, you have to argue that without symmetry, it's trivial, but that's.
So how about higher dimension generalization? One can also find analogous extend operators and.
Yeah, so in higher dimension, you will have to consider higher dimensional extended operators, as you said. And then you might have to go down the hierarchy a few times. And that will, this is explained in this paper by Els and Nayak, even though they discuss a boundary, but it's the same idea.
Is the idea the same as domain wall declaration construction to SPT then?
Yeah, this is essentially equivalent to domain wall declaration. We just kind of reverse the logic. We actually start from a state putting defects instead of first breaking the symmetry and add them up. This is starting from a symmetric state, but then introduce defects. But it's equivalent in the end of the day. Sure. All right, so now I'll move on to a slightly more detailed discussion of mixed states. Okay, so well, we all learn from quantum mechanics that a generic quantum state is represented by a Hermitian positive semi-definite operator rho, which is a density matrix, and this trace should be 1. For pure state, psi, the rho is just projector to a ground to that state. And any mixed state, you can diagonalize the density matrix and write it as an ensemble incoherent superposition of these pure states. And there are many things we can say about the mixed states, but I just want to have these two statements. So first, any mixed state has a purification. So that means any mixed state can be thought of as describing a subsystem of some pure states, which you can easily prove from the spectral decomposition of mixed states. And second, there's a way to sum, we can form convex sum or make density operators, basically summing over different density matrices with weight between 0 and 1, and the weight adds up to 1, and you still get a density matrix. Okay. All right, so these are the most general quantum states. And for pure states, we know the time evolution are given by unitary operators. So that should also be generalized to mixed states. So the appropriate generalization are the quantum channels. So this is what I just said. In closed system, the time evolution described by unitary operators, and for an open system that's or like a mixed state, time evolution is generally not unitary. I mean, it's just usually not unitary, and it's not invertible, and it should be described by a quantum channel. So the mathematical definition of quantum channel is the following. So we have some density matrix, and we sum up, the conjugation of density matrix by the cross operators, and which should satisfy this condition. But a better way to think about it is probably in terms of a purification. So any quantum channel can be purified into a unitary acting on the larger system. So we add some ancilla. Ancilla is in some state of ancilla, okay? And apply a unitary to system plus these ancillas. Okay, so we get some new states, and then we trace out the ancilla, which will give us whatever this channel, well, this will give us this channel. Okay, so we can always purify it into a unitary. So it's basically unitary evolution on a larger system, but then we forget about the ancillas of the environment. Yeah.
Are there constraints on the size of these ancillas? Like, does it just have to be a qubit? Is that to be the size of your original system? Or?
I mean, there's really no constraints on the size. If your system could be very large and you have just one qubit and you entangle them in some way,
and that's enough to recover all the possible.
Oh, well, so if there's no notion of locality, then this is fine. We don't have to worry. You might have to have a large enough dimension of ancilla to do anything we want, but later on, eventually we want to think about local systems. So then the ancilla is also extensive. All right. So let me discuss a particular example of a decoherent quantum state by a quantum channel, just to in case you're not familiar with this. Quantum channels, like that's my status half a year ago. So I like to just really explicitly write out what it looks like in the spin chain, in the many-body system. Okay. So suppose I have a system of n qubits, okay, and with Pauli operators xi and zi as usual. Now, here is an example of a local quantum channel, meaning that you have some ancilla and then there's some local interaction between system ancilla. Okay. And we can get a quantum channel that looks like this. So it's a product of channels acting on each side, sort of, and the single side channel acts on density matrix in this particular way. Okay. Now, if you expand out this whole channel acting on rho, we get basically all possible combinations of zi, zj, zi, zj, zk, etc., conjugate acting on rho, and with some probability in front. So we get a huge sum of possible states, acted by Z, essentially. Okay. Now, suppose this rho represents some gap ground state, or just some ground state of the Hamiltonian, of some Hamiltonian. Then these Z's will create some excitations on the state. And if you apply two Z's, will create multiple excitations, etc. So this channel epsilon rho is just a convex sum. Each of them is a density matrix, is a convex sum of shallow local unitary deformations of the side. Okay, to just create some excitations here and there, but locally. So if this is indeed a gap ground state, then we know by deforming this state with the local unitary, we stay in the same phase, okay, even though it's deformed. So in some sense, all states in this ensemble, all of these states in the ensemble, they belong to the same phase as psi. So we have an ensemble of states deformed in all possible ways by Z. I think this is a useful picture to visualize what these states are. Okay. Now, this P is a number between 0 and 1, so it's a probability. And there's, in some sense, there's the strongest channel at P equals 1/2, where the error, this is like the noise that occurs just with equal probability, with probability 1/2. Okay. In that case, all of these numbers are exactly the same, so we just get an equal weight superposition of all of these possible deformations of the state by locally acting Z's everywhere.
Can I ask you a question on this?
Yeah.
So you say this is a sum of shallow local unitary deformations, but the ones you've written are local. But if you continue the summation, once you get out all the way to the end, you're going to have these very long strings.
Oh, they're very long, but they're still shallow, right?
All right.
So here, just because, okay, so here's because I choose a very simple operator Z, which all commutes.
Mm-hmm.
So even you apply all the Z at once to a system, it's just one.
Yeah.
So in that sense, it's shallow. I mean, it could be very non-local, but it's shallow, right? It's finite depths. Yeah, but if these Z's are not commuting, then no, this is different.
I guess if you put X's in there,
You could-
then it would be
If you just put X, it's still the same, but then you can have other things. Sure.
Z's index.
Right. Yes, absolutely. Yes. All right. Okay, so this is what a kind of decoherent quantum state looks like. It's just messed up. You messed it up with some excitations. Now, since we're talking about symmetry-protected phase, we have to first really think clearly about what symmetries are for mixed states. Okay. Here, it comes in a very important distinction between two kinds of symmetries in mixed states, which I think they go under the name of strong and weak symmetries in some literature. So we should always remember the mixed state is your system plus environment, and tracing out the environment. Now, a strong symmetry means the coupling between the system and environment preserve the symmetry of the system exactly. So if you imagine you have U1 symmetry, then say electron and phonons, then obviously coupling is going to preserve the U1 charge exactly, right? You cannot just get out the electron into vast of phonons. So if that's the case, then we say the symmetry is strong. Mathematically, you can write this condition that the U symmetry transformation, when you multiply it on rho, the density matrix, from one side, this is somewhat unusual, we get back the density matrix up to an overall phase. Okay.
Is the symmetry assumed to be abelian?
No, but you can get, it's a unitary acting on the rho, so you can get back at least at most the phase. It doesn't, yeah, so far I'm not talking about the group structure. This is a single transformation. Okay, more concretely, if you expand this rho into as ensemble of pure states, then you acting on each state in the ensemble, this state should be eigenstate with the same phase vector. So all of them have the same vector. They are all eigenstates with the same vector. Okay. Now, if it sounds unfamiliar, then it's actually there's a familiar example of a strong symmetry. So we learn in STEM that we have these canonical ensembles. which is a system of particles coupled to a thermal bath. But it's only a thermal bath. The number of particles cannot change. We cannot have fluctuation of particles numbers. In that case, the number conservation of these particles, is a strong symmetry. Okay, so it's just symmetry of a canonical ensemble, basically. All right, so there's strong, there's also weak. The weak means the system and the environment can exchange charges of symmetry. So the symmetry is actually extended to the ancillars or environment as well. In that case, mathematically, we have U rho, U dagger equals rho. So this is more like a canonical way of how a symmetry should transform rho. Okay? And this is one way to have weak symmetry. That is, you still expand it in some eigenstates, some pure states. And these pure states, they are still eigenstates of U, but then they have different faces under the action of U. Okay? In that case, if you conjugate the rho from both sides, these faces will cancel and we get back the same density matrix. Again, we have a familiar example from STEMAC. This is just grand canonical ensemble, right? Now, we know, I guess, I don't know why I wrote symmetry plus the system plus thermal and particle baths. This is how we get grand canonical ensemble. In that case, U1 is a weak symmetry. The particle number conservation is a weak symmetry. Okay, so there are some symmetries which are always weak. Just doesn't make sense to add a symmetry alone on a system. For example, translation or any spatial symmetry. Couplings only preserve the symmetry if you translate the system and the environment together. So that's always weak. And so is time reversal, because time reversal acts on everything, the complex conjugation acts on everything. But internal symmetries like U1 could be strong. Okay. All right, so this is kind of a setup. We have these different mixed states. I haven't told you what exactly are the mixed states that we should consider, but roughly they will be like the pure state subject to noise, subject to some quantum channel, local quantum channel. Okay. So now let's consider a concrete example of kind of SPT in mixed state. So the obvious thing to do is that you start from SPT in pure state that we already know, like a cluster state. And now we subject it to some noise. Suppose that there's some noise and it becomes a mixed state. You can ask whether there's still some topology left. There's something non-trivial left in this mixed state. Okay, so just this is the same thing that you've seen before on the cluster state on the spin chain. And now I want to subject it to this channel that couples to Z. The Krauss operators are Z to I on the red sides, I guess, Z to I. Okay, not on the blue sides, only on the red sides. And apply this channel to the ground state of the cluster state model, then we get this particular mixed state. Okay. Now you can check that once you apply this channel, the Z changes the charge of X on the red sides. Basically, it allows exchange of charge between the red sides and the environment. So the red X becomes weak, but the blue X is not touched by the channel, so it remains a strong symmetry. And in general, as you saw a few slides ago, the density matrix of the decoherent state is very complicated. But when we go to this limit of p equals 1/2, the kind of strongest channel, the maximal strength, then there's a simple expression of the mixed state. It's just the product of these projectors. Okay. So the ground state has these projectors and also the one with blue and red switched. But the channel kills half of it, and we're left with half of the projectors. And that's why we get a mixed state. There are not enough projectors to really define ground state, and we get a mixed state in that space, defined by these projectors. All right, and we can still write down the string order in this mixed state. So O is a product of, it's the same O that I showed earlier. So it's a product of X in some interval decorated by the two blue Z's on the two edges. And this O still, this X, red X is a weak symmetry. So this O, X on row by conjugation, and now even the truncated version X on row and returns the row back. So we can say this is a string order. So pictorially or heuristically, we say that the X symmetry, the weak X symmetry, is defect is charged under the strong blue X. Okay. All right. So it's also kind of instructive to think about it in terms of this wave function picture. So you start from a superposition of these domain wall states, the equal wave superposition of domain wall state. That's a ground state. That's a wave function of the cluster state. And now we turn on this channel, and let's go to this maximal strands p equals 1/2. What happens that it basically, decohere all of this, it destroys the coherence between all of these different domain wall states. They're no longer coherent superposition, and all we have is an incoherent superposition in the space of, in the space of decorated domain wall states. We have equal weight mixture of these states. Okay. So the only non-trivial feature here is really just the fact that we have decorated domain walls, and they are lumped together in ensemble. All right. So this is another kind of useful thing to keep in mind about mixed state, or about this kind of mixed state, especially weak symmetry, is that the domain walls or the defects of the weak symmetry, so the up and downs, they are really classical. They enter the mixed state just as a classical mixture. So they do not carry any coherent phase information. Unlike in the ground state where we have superposition of these domain wall states, then it actually matters what are the relative phases between different states. Here, they're just a classical mixture, so they don't carry any coherent phase information. All right. So now, we should define what we really mean by having some phase or SPT in weak state. Okay. So the definition, of course, here's one definition which appears very natural. Okay. Of course, it's not the only definition. It doesn't mean that this is like the only way to define the notion of SPT in mixed state, but this is one natural definition that includes all the examples that we've studied so far. Okay. So the motivation is to include all states of this form. You start from some ground state and apply some local quantum channel. So you get something that's mixed, but it's not too far from ground state. It's like you just go from ground state a little bit into the world of realm of mixed state. Okay. The psi is a gap ground state. So here's a definition that captures all such states. If I have a mixed state that is short-range entangled, then it means this mixed state can be purified into a short-range entangled pure state. Just like here, rho can be purified into the gap ground state. Okay, so that's gonna be my definition of mixed state. Basically, these are the mixed state I want to study. Okay. And we also need a notional equivalence between different mixed states. So in the ground state, we know the equivalence is given by unitary operators. And unit operators, one nice thing about unitarity is that it's invertible. We can have U, and U inverse is inverse time evolution. Okay. So naturally, we would like to generalize this to mixed state, replacing unitary evolution with the possibly dissipative evolution or quantum channel. But then there's a problem. Dissipation is not invertible. Right? We know that from thermodynamics, or some kind of law of thermodynamics. So you cannot just say, there's a channel that takes you from this state to that state. It doesn't mean that you can go back. But equivalence is really two-way. Right? In order to have equivalence relation, you have to be able to go between the two states in both ways. Otherwise, you don't get an equivalence. So a natural definition is then to demand a two-way sort of connectivity between the states by quantum channels. Of course, these two quantum channels, they are not necessarily the same, they can be different. And these are local quantum channels, local in the sense that they are of sublinear depths, sublinear in system size. Okay, you don't have to demand finite depths. That's a bit too much. Sublinear is enough. Meaning that if you purify it, it's a sublinear depth unitary, local unitary acting on system plus environment. Yes.
So if you have only those two definitions involved, what if you didn't have the top line of your slide about also requiring that it came from the line above, requiring that it came from decohering a pure state?
So the questions, we can have this equivalent relation, and what if I don't demand they are?
Maybe I misunderstood. So you have actually three things on your slide: the Grotz relation, the
Yes.
entangled mixed states,
Right.
and then the top line is saying where you only want to study cases that came from.
Okay. So yeah. So I'm not saying that I only want to study these states. I think this definition captures all five states. It's not. I'm not sure it's equivalent. I think it's equivalent, but okay. I think it's equivalent, but let me say a safe thing, that is, no, this definition includes all such states. Okay. It also includes things like, you just take a quantum state and trace out part of it, or you measure out part of it, which you can probably also do with a channel. I think it's equivalent. But...
So we are still in the sense. So I think the top line where you have the ground state and you have a little channel, I guess that could go to a critical point.
The other thing that this doesn't have to be a gap ground state to begin with, right? So you can apply the quantum channel. You might get also a short-range entangled mixed state.
But you're saying anything that satisfies the definition of short-range entangled mixed state can be obtained
from some gap ground state.
Okay.
I think so. Yeah. I think there was another question.
Yeah, feel free to ask.
Yeah. Right. Anything, please ask. Oops, what happened?
Not personal question.
Wait. Yeah, I answer, but maybe not the answer you want. Anyway, so again, we always need to specify what we mean by trivial, and this is the same definition of trivial. It's a tensor product state with a given symmetry. All right, so this definition was first proposed in this paper, as far as I can tell, and was later a very recent paper sort of further developed this definition in the context of long-range entangled state. So let's now explore the consequence of having this definition. First, there's just with the definition of equivalent relation, there's an interesting consequence already. So in the world of pure states, ground states, we know there are these class of ground states which are called invertible phases. They are not protected by any symmetry. They're still non-trivial. They're distinct from product state, not protected by any symmetry. Example of that is a P plus IP superconductor or Majorana chain in one dimension. Or in the world of in the bosonic system, that will be an EA state in 2 plus 1D. Okay. So one consequence of having the definition of mixed state, equivalence of mixed state, is that any invertible state, any bosonic invertible state with only weak symmetry are all trivial. So we can forget about all these invertible phase. So here's an argument. Let's say psi is an invertible state. Okay, say the EA state. So I'm going to draw some pictures. So this is going to represent this state psi. And we're going to introduce some ancilla, represents the environment, extensive system as an environment. So I want to find two quantum channels. One takes this state to a trivial state. The other one create this state out of a trivial state. So let me first show the one way, the direction that goes from this state to a trivial state. That's very easy, just swap the system with the environment. literally just swap them. That's a unitary operation. Okay. And then we can discard the environment, trace out the environment, and just left with a trivial product state in the system. But this you can do for any quantum state. So that's why it's not enough to demand one-way equivalence. We need the other way as well. So the other way is a little more involved. We start from a system which is the black dots and the environment, the red dots. The system is, they are both initialized in some tensor product trivial state. Okay. And now let's first look at the system here. By the definition of this invertible phase, we know we can create E8 and its inverse, the image, the mirror image of E8 out of a trivial state by some finite depth local interpret, by adiabatic evolution, basically. So that's psi and psi star. Star is the mirror image, the time reversal image. Okay, and then there's also the environment, which hasn't really, nothing has happened to it. But then we can swap the inverse into the environment and trace it out, just as what we did earlier. And now we're left with the E8 state, together with some trivial product state in the system. Okay, so these are the two quantum channels. One destroying the E8 state, one creating the E8 state out of trivial state. So we conclude that the E8 state, by this definition, is two-way connected to a trivial state. Yes.
Is there a reason you didn't directly use the unitary on the environment? You know what I mean? Like, is there a reason you didn't use the black and red dot to then apply a local unitary, rather than first applying the local unitary within the black dot and then do the swap?
I mean,
getting psi star directly on the red.
I guess so. I mean, okay, you could do that, but you can just combine these two as one unitary. I just want to show you step by step. Is that what you? Okay. Yeah, I can just combine all of them in one unitary. Sure. So the same argument works if you start from some pure state with weak symmetry, because for ground state we don't really need to distinguish weak and strong. But now once it's made into a weak symmetry, then you can swap it into the environment. You always swap into environment or create it from the environment this way. So the same argument works for any SPT with weak symmetry, any invertible state with a weak symmetry. So no, if you only have weak symmetry or you have no symmetry, then there's nothing interesting going on. Basically, that's the conclusion. This was discussed in this paper by Roach and Chong. All right. So we need some strong symmetry. I think the lesson that the quantumness is encoded in strong symmetry. Strong symmetry keeps track of some quantum mechanical superposition property, the phase information. This phase is all it's about for SPT. So we need some strong symmetry. All right. So now let me get back to the example of cluster state to show that if we have some strong symmetry, then this thing is still interesting, or no, there's some non-trivialness about this state. Again, this is the third time I show the Hamiltonian. This is a cluster state, and apply this quantum channel that which makes X a weak symmetry, and we get this state at the maximal strength. And I guess I've shown this slide exactly before. This is copied. So, okay, wait. What I want to say that with this characterization in terms of a string operator, one can show, so I'm not going to go through it, that this state cannot be connected to a trivial product state, okay, just because there are these strong charges. Okay. All right. Okay, so there's something left when you have a strong symmetry that prevent. Yes.
Yeah, but is there any way of actually measuring the string order right here? Because like what you've written isn't, I mean, O is an operator, but you're acting on it from the left and from the right. So is there a way to actually, if you had this density matrix, can you measure this long range string order with some observable?
Not for this one though. Well, we can in the same system. There's also a blue O, which is just switch blue and red. So the blue X and then the red Z on both sides. So that's also string order in this system. That we can measure. Right. Not for this one. For this one, you need to probably measure some sort of range too, but that's not physical. But for the strong one, you can measure. All right. So the general kind of pattern is that if you have both weak and strong, if you have just strong, then of course, you can have everything that just from strong symmetry, you can have SPT, and they are going to be robust, at least under a channel that's not too severe to destroy the whole state. Okay, but in general, you need some kind of weak and strong symmetry together to have some sort of interplay to have interesting mixed states. So here I'm going to discuss a classification using these ideas, just basically trying to take the examples and I just discussed and make it more general. So here's a general setup. I have a weak symmetry, which I call G, and there's some strong symmetry, which I call A. Okay. Now you can convince yourself that A is always going to be, so together you have a G tilde, which includes both G and A. In many cases, G is just G tilde, just G times A, like on the previous slide, Z2 cross Z2, but it doesn't have to be the case. It could be the weak symmetry is somewhat, G tilde is somewhat a non-trivial extension of G by A. Okay, that's possible. And in general, they fit into this kind of structure. So A is a normal subgroup, and G weak is a quotient of the total symmetry group by A.
Already this way, usually a normal subgroup is gaugeable, but the quotient group is not.
Mhm.
It's a non-trivial extension. So does it mean the strong symmetry can always be gauged, while the weak one may or may not be gaugeable?
Well, so for the weak one, you are even before looking at extension, we have to ask what does it mean to gauge a weak symmetry, right? So we can already ask that question before talking about extension, right? So you have to gauge a weak symmetry as like a classical gauge theory, basically. A strong symmetry can gauge it as a quantum gauge theory. And then there's if you have extension, there's some interesting sort of mixture between the two kind of structure. All right. Okay. Now I have to make an assumption, which is not at this point, this might not be very well justified. I have a definition of short-range entangled mixed states, and I'm going to, for now, assume that this argument of symmetry localization works for such states. Okay, I'm going to assume this. And see what we get. Once we assume this symmetry localization, then we can talk about decorated domain wall, basically. Okay. And then we can play the same game. And so here I'm going to list the 3 possible options available in 1+1D. So this is 1+1. You just want to use 1+1D to illustrate what's going on. Higher dimensions are, again, they are similar, but they are just more complicated. So if you forget about the weak symmetry, there's SPT protected by the strong symmetry. And you can imagine they are not going to be affected too much by coupling to environment as long as the strong symmetry is preserved. Okay, so it's going to be an element of this H of 2 of A, and then there's an additional condition, but that's okay. So let me talk about them later. And then there's a second thing. That's you have some weak symmetry defect. We can ask what's the charge of that defect? The unitary we attach to the end, the decoration, how is that charged? What's the charge of that decorated unitary operator under the strong symmetry A? It's going to be classified by some map from G to A hat. Anyway, so this is just a charge of the decorated unitary operator of G defect. And we just argue that if you only have a weak symmetry, there's no SPT order. We can find these channels to destroy this state. Well, to trivialize this state. All right. So this resembles very closely the classification of SPT when both G and A were strong. So this is basically modeled on that. If both were strong, then we can also have these 3 features. one is SPT protected by A alone. The other one is a G defect charge under A. The last one is SPT protected by G alone. Okay. So all of them were meaningful if both G and A were strong symmetries. But now this is not enough. So just give me some SPT protected by A. If there was no G symmetry, that's the end of story. But now we want to make sure that this SPT protected by A with some features, it's compatible with the G symmetry, with having G symmetry. Okay, it's not obvious that it's compatible. And again, same thing for the second line. If you want to have this particular pattern declaration given by this chi, we have to ask whether it's actually compatible. It's a consistent physical realization, that whether there is a physical realization of this declaration pattern. Okay, so the question is whether, yes.
This may be a very foolish question, but why do we need to have a weak symmetry, or at least a weak symmetry from the Hamiltonian composed? If you have a density operator, it always has hermiticity requirements, right?
Right.
And that should impose a symmetry which, at least from my understanding, wouldn't fall under the strong symmetry classification. So like hermiticity is some like S2 or something.
Hermiticity is just the symmetry. Yeah, it's okay. So let me try to understand your question. The question is, dense symmetry is Hermitian.
Yeah.
And you want to think of it as a symmetry.
Mm-hmm.
And does that give you any SPT? Just based on that symmetry alone.
Well, that and a strong symmetry.
Maybe, and that with some strong symmetry. Yeah. Right. So in some unpublished work of Ruochen, you can formulate this question as going to the double state representation of mixed state, the Choi representation, Choi, and the longer name which I cannot pronounce. I'm sorry. And ask, and that in that case, hermiticity becomes just an anti-unitary symmetry. And naively, you can have SPT protected by that for the double state. But it turns out that the SPT cannot be mixed state, cannot be actual mixed state because it violates positivity. Mm-hmm. So basically, it does not occur. Right. Although here I'm not including that hermiticity as a symmetry. G is some physical symmetry. Right. But I think that's in the work of Ruochen, some unpublished work. Yeah. All right, so let me get back to the question of whether these things are well defined. We can say these things, but are they actually physically realized? Okay. And this is captured by a few conditions on these data, but we can imagine these are just some data and want to check whether they are physically consistent or not. So for example, in the first case, whether ASPT is actually consistent with the G symmetry, the way to check is to consider a junction operator. Basically, you have two defects and you just kind of fuse them, whether the junction operator is charged or not under A. Okay. If it's charged, then this is not work. This is not going to work. So this is one consistency. And this is really about a symmetry charge under a strong symmetry. You can imagine even for mixed state, this is going to be relevant. The second condition is a little more subtle. We consider not just a junction, but really two junctions coming from three defects, fusing into one. So imagine you have three defects and fuse them in two different orders, and then you should get the same result. But the two ordering of fusion, they could differ by a phase factor. Okay. If that phase factor is somewhat non-trivial in some appropriate definition, then this is also not consistent. Okay. But this is about phase factor. So you can imagine this is this one is it should be gone once we consider mixed state, because the G defects are just classical mixture. There's no information about phase factors. All right. So now I just take the same slide and change some of them to red to indicate that these things are no longer relevant for mixed states. So I've already discussed that a weak symmetry alone SPT is not is trivial for mixed states. And this condition that demands the junction having no charge on the A, this is about the charge of a strong symmetry. So this is still well defined. We still have to impose this condition. But then the next one is about the phase vector in this kind of local deformation of defects. It's F move in 1D. And this is phase vector, so it's going to be, well, we do not have to keep track of it in mixed states. Okay, so all the rest things are irrelevant for mixed states. All right, so now we get just a different classification. Go back. In some sense, we lose something. We lose this third option, which was there for both G and A being strong symmetry. We also gain something possibly because we drop one constraint. So one constraint is released, even though we lose something. So it's just a different classification now. And that allows a possibility of having something that has no analog in the world of ground state. Okay, meaning that not everything comes from just starting from a ground state SPT and then you put some decoherence. That would be somewhat less interesting. There's something that cannot be purified into a SPT with the same symmetries. Okay. So here's one example, just the simplest one that we can think of, might not be the most physically relevant one, but no, here's an example. So again, I'll have two Z2 symmetries, one strong, one weak, but then instead of Z2 cross Z2, they actually fit into an extension into a Z4. Okay. So the weak Z2 symmetry, the generator squares into a strong symmetry. All right. Now let's consider the SPT, pretending that you forget about the Z4, and we have SPT where the Z2 defect, one of the Z2 defect carries a charge under the other one. Okay, so that's kind of like the analog of the cluster state, except that the symmetry structure is different. And both were strong symmetry. It's just a Z4 symmetry, and we know Z4 has no projector representation. So there shouldn't be any SPT in ground state, but if we literally follow this kind of domain wall declaration, then there's something wrong with this declaration, and that something wrong is this F move. The phase vector is non-trivial. Okay. So this was obstructed in the case of ground state. But it's possible to have this declaration when one of Z2 is weak, okay? And we can realize it in exactly solvable lattice model, just to really know that the existence. And because of this reason, there's no symmetric short-range entangled purification of this state. It just doesn't come from any short-range entangled symmetric state under the coherence. Now, there's indeed asymmetric purification, but it's actually into a gapless SPT as studied by Rubin in this paper. Okay. So you start from this gapless SPT and you turn on some noise and you can reach this mixed state. Okay. The claim is that the only symmetric purification is the gapless one. Or you can purify it into a symmetry breaking state. All right. Oops, what happened? So for those who are into field theory, this is some explanation using the field theory language. So let's see where the obstruction came from in the when both are strong. So A is the would-be strong symmetry and B is the would-be weak symmetry. And the Z4 means there's some relation between the background gauge field that's given by the delta A equals B squared, and B is closed. Okay, so A is not closed. And the declaration pattern is given by this particular action, which should be closed as the topological response, but it's actually not. And the kind of non-closedness is given by this term, which only involves the weak symmetry, the would-be weak symmetry. So now it's weak, and this is some phase vector, and it's no longer important. Here's a kind of a related argument that B is, because the charge of B is not really conserved in the system, it has a trivial time component, and this action is always trivial if a B has no time component. All right. Okay, so let me see how much I'm doing on time. I'm already almost approaching 11:30. So let me briefly discuss the general mathematical structure behind this story. So okay, this is just to to kind of to summarize what the general theory is. So there's strong and weak symmetry fitting to some kind of exact sequence, short exact sequence, a group extension. And then we basically take the generalized cohomology classification of G tilde SPTs and examine the various parts of it. Which ones are relevant, which ones are still preserved in mixed state, which ones are not. And then we can get the classification. Okay. So there are the defects declaration are described by the E2 page of the spectral sequence. And there are various obstructions computed by differentials. And some of them represent surface obstruction, which are irrelevant for mixed states. So that's a modification that we have to make. And then we have to sort of distinguish a little bit between fermion and boson. Okay, but hopefully this gives you a general picture of what's happening. All right. Okay, so it looks nice. Looks like we have some sort of idea of what's going on. But remember, all of this is based on the assumption that the symmetry is localizable. We can localize the symmetry. Okay, and for a long time we thought the definition of short-range entangled state would imply this localization property because we assume the short-range entangled mixed state, I mean, by definition, it can be purified into a short-range entangled pure state. And we know short-range entangled pure state, you can localize the symmetry. Okay, but it turns out that it's not quite the case. This question turns out to be somewhat subtle. So I'll use the last few minutes to discuss this issue of whether a symmetry is localizable in the kind of states that we want to study, short-range entangled mixed state. Okay, it turns out that this definition does not quite guarantee localizability of short-range entangles of symmetry. Okay? And just to remind you, the definition is the definition that the mixed state can be purified into a short-range entangled pure state. Okay? And here's a counterexample. So let's consider a one-dimensional chain of qubits. Again, just chain of qubits. And let's say there's a strong Z2 symmetry X, which is a product of all the X on each site. And let me consider the following density matrix. The rho is proportional up to some normalization factor to 1 plus X. What does it mean? Well, it means that in the eigenbasis of X, which I denote as a bit string of little x is 1 or minus 1, this is just the identity operator when the total X is 1, otherwise it's 0. So you only include states which have total X charge equal to 1 in the sum and with equal weight, and no other states. Okay. So physically, this is kind of like just randomly distributing X charge everywhere in the system, a bit like an Anderson insulator. I mean, in quotes, this is the sort of ensemble. But in this basis, it looks like an Anderson insulator of X charges. Just spread it out any way you like, but keeping the total charge even. Just fix the overall charge. Okay. Now, the somewhat unexpected thing that this is actually a symmetric, strong Z2 symmetric SRE state, meaning that you can purify it, preserving this strong Z2 symmetry into a pure state, the ground state of something. In fact, you can purify it into a cluster state. But then you can show that X is not localizable on rho, because there are just too much fluctuations of charge. When the symmetry is localizable, means that the charge fluctuation only comes from the boundary of the region, but here it's just fluctuates independently inside the region, so you cannot localize the symmetry. And we can also show this more carefully.
Okay.
Yes.
So once you go to the purification, in that case, right, by definition, you can localize, but I guess the point is you cancel it back to somehow. Is it acting on the X because the film you use to purify?
Yeah, exactly. So though the decorated operator is actually in the environment, you trace it out. So to purify it, for example, I can introduce some additional spins, which are like these, domain law degree of freedom to keep track of charge. But then once you trace it out, the information is gone entirely.
But doesn't it almost raise the opposite? Like, it's almost surprising that there's a state where you can put it, how to say, it almost makes it up. The ones where you can localize is surprising because you should generally expect to always have to use the environment perhaps once you bring the short entangled purified state and then localize. It seems hard to avoid using the environment.
Yeah, but no, it's hard not to use the environment at all. But sometimes, most of the time, I'm not sure it's most of the time, but in many other cases, the operator still has some weight in the system.
As long as there's some weight.
I think some weight is enough. Yeah, but here it's like the entire operator supported on the environment and trace out, right? So yeah, I found this quite unexpected that you can actually purify it into a short-range entangled state. Anyway, so there's a third feature that's somewhat interesting, that rho is locally indistinguishable from just the maximally mixed state. One, if you look at any region in a system, you just have random X charge and no conservation of charge anyhow. Okay. Another way to say this is that if you take out one spin, then it becomes a maximum mixed state. And now for this state, X is weak. So it's locally indistinguishable from a state with only weak symmetry. So in some sense, rho resembles a non-invertible state. There are some other states which are locally indistinguishable from this state. Okay. Now let's recall what happens in a symmetry breaking state. So I want to claim that this is some sort of symmetry breaking state. So let's recall the features of symmetry breaking state. So again, I'll use the same spin chain, but now the ground state, the same symmetry. The spontaneous symmetry breaking state for the X symmetry is let's consider cat state to preserve the symmetry. So it's all spin up plus all spin down, or all spin up minus all spin down. Okay. And if you write this in the X basis, usually we write in the Z basis. In the X basis, it actually becomes this very similar analogous sum of just X charge states everywhere, fixing the global charge. Okay. But here it's a coherent superposition, it's not a mixture. And these two states are locally indistinguishable. If you look at the local region, you just get a maximum mixed state between all up and all down. You don't have any information of the global charge. Okay. And of course, in this case, we know these cat states are long-range correlated. The Z operators have long-range correlation, and they are not invertible states. So we wouldn't consider them in the classification for various reasons. There's long-range correlation, they are spontaneous symmetry breaking, and all that. Okay, so just by analogy, we will call this 1 plus X density matrix as a spontaneous symmetry breaking, spontaneous breaking of strong symmetry to a weak symmetry. Okay. For the following reasons. This is a state that I showed earlier. Well, it has a strong symmetry to begin with, okay? But it's locally indistinguishable from a state with only weak symmetry, that's rho equals 1. So in this sense, the strong symmetry is not there. It's really this, we should really think of it as a weak, one that where the strong symmetry is spontaneously broken to weak. We can also make it a little more precise. That is, using some local correlation function, local operator. For example, rho has only short-range correlation function for any local operator, including Z. If you calculate Zi, Zj for rho, or any Zi, Zj, Zk, whatever, you get 0. Okay. The only, well, okay, that's the statement one. The second one is, if you consider a Renyi 2 correlator of Zi, Zj, it actually has long-range correlation. And this follows trivially from Zi, Zj actually commutes with X. Okay. And normalize it by trace rho square. You can also think about it in the Choi representation of the double state. You can literally write it as a cat state in a double state where the strong symmetry, which acts on one side, is broken down to a symmetry, diagonal symmetry that acts on both copies. So in that case, it's even more clear that it's a strong weak symmetry. strong to weak SSB. So this was discussed by Zhongyang and Chaoming and Senker in this paper, and also clarified in our recent update. All right, so we have to basically lessons that we have to add some additional condition to make sure that we can discuss localization of symmetry and to apply this whole decorated domain wall idea. So the condition that we came up with is to demand some version of invertibility of state. So I'll be very brief. This is almost the last slide. So rho is invertible, symmetrically invertible, if there exists another rho, tilde, different rho, tilde, they're generally different rho, tilde, such that the tensor product is equivalent, by this two-way connectivity of by the quantum channel to a trivial state, preserving the symmetry. So we can argue that 1 plus x, this one that causes us trouble, is not symmetrically invertible, even though it's actually invertible in the absence of symmetry. But demanding the symmetry, it's not invertible. Now, once we impose the invertibility, symmetric invertibility condition, then we can argue that the symmetry is now localizable. Okay, and then we can apply this classification scheme.
Right?
Yeah.
There's a reason you don't want to. On the previous slide, you were pointing out interpretation terms within the symmetry breaking from strong to weak.
Right.
I could have imagined you said, well, let's exclude symmetry breaking state.
Right.
Is that equivalent, or is there a reason you prefer this, or is there a different?
Right. So there are these two conditions. So in the world of pure state, we know, at least in 1 plus 1D, the SSB is the only obstruction to invertibility. Now, in mixed state, so I think this is something that we still don't fully understand. The strong to weak SSB is one obstruction to invertibility, but there are other obstructions. There could be other obstructions. I think we know examples where it has no strong to weak, but it's not invertible. But I don't feel like I'm ready to discuss it here. But let's consider this as a separate condition. We can show that, well, you can show that if you have strong to weak SSB, then it's definitely not invertible. So it's kind of sufficient, but not necessary, I guess. But anyway, so if we add this condition, then we can fix the problem, which is natural because short-range entangled states, the operational definition is also in terms of invertibility. So we're just generalizing what we do in ground state. All right, so I think I should stop. Here's a summary. So I guess the lessons that there's interesting topology in mixed states. Okay, and I guess we still know very little about them. For SPT, we can do something based on generalizing the decorated defect, decorated domain wall. And there are examples which just have no pure state analog. Okay, here are a couple of things that are related, but I don't have time to discuss. Okay, so I'll stop here. Thanks for attention.
Meng?
Oh, so Max, I'll have Ruben first ask her.
Sorry, I didn't hear.
All right, maybe Ruben, you should go first since you started already.
That's still a question. Can I ask, so is it clear, should I think of this classification as a conjecture, or have you proven that it's complete? Even with, let's take this condition of invertible.
Let's say it's a conjecture for now.
Okay,
yeah, it's not at the same status as like the NPS classification of 1D SPT. For sure, it's not in that status yet. Yeah, although I believe it's a complete classification once assume certain appropriate invertibility. But no, I feel like at least I still don't fully understand the landscape very well yet. Like this invertibility condition is something we realized fairly recently, so it might change like tomorrow. Okay, maybe Max. Also Fiona, I saw the hands up.
I'm muted. Man, thank you very much. Great talk. So one question. If I confine myself to the realm of this Hamiltonians with disorder, where disorder is breaks the symmetry but is on average symmetric. Is, is there something special in that realm, or do you think it's just equivalent to more general mixed?
Let me say a few words about it. This could be so there's a similar story in Hamiltonian with disorder. There's a quench disorder, ensemble of ground states. The biggest difference is that in that case, we can formally write the ensemble as a density matrix. But the important thing is that in that case, we have a preferred basis for the density matrix. It's just a ground state of these Hamiltonians with a particular disorder realization. But for general density matrix, I can change bases any way I like. Okay. And another difference is this density matrix, the equivalence is in terms of quantum channel. But the Hamiltonian, if you have a Hamiltonian, there's a very natural definition of equivalence in terms of adiabatic evolution, just applied to the ensemble. So the equivalence relation is different. The invertible states remain non-trivial for disorder system. If you add disorder to E8, it's going to remain E8. So that's already one big difference. And another difference, but one common feature that, in the disorder ensemble, of course, we don't have any phase information as well. So all of these obstructions are gone. That's the same. But there's another interesting feature that's possible in a disorder ensemble, but not in a mixed state. That is, we can have an Anderson insulator. This 1 plus x we consider non-invertible state for mixed state for various reasons. But if we have an Anderson insulator, we consider it as a short-range entangled disorder ensemble. Okay. That changes the classification even more dramatically.
I see. And so is that story, do you feel like that story is understood, or it's still?
Well, I guess we understand some parts of it, some aspects of it. I cannot claim that this is a rigorous full story, but I think we understand some aspects of it. For the short-range entangled states, at least.
Thank you.
Fiona, I saw your hands up.
Yeah, I was wondering if you can, so to make this classification, you mentioned that this sort of two-way thing was important, right?
Yeah.
And I wondered whether you could comment at all about, suppose that I want to know whether I can realize, some of these topologically non-trivial things, as like, how to say, suppose that I want to use a criterion of stability that is like, I can write down a quantum channel that satisfies certain conditions for which this is a steady state. Does your classification, do you know what those conditions would be? Or is that a completely unrelated?
So suppose, so we have some definition of short-range entangled mixed states. And your question is more about the steady state. So I want to realize a steady state of some Lindbladian, for example.
Right. Or I might say, what are the conditions on the Lindbladian or on the channel, such that states in your classification are not connected to the trivial state. Non-trivial states in your classification are not connected to the trivial state.
Okay. Well, so I guess the question is, do we have some topological variants to distinguish different classes, right?
Right, that are invariants under the Lindbladian flow under certain conditions. Yes.
Right, because in the Lindbladian flow is, for this purpose, is more or less equivalent to the two-way quantum channel. If you have a Lindbladian that going evolution from one to another and then back, then it's more or less the same as two-way quantum channel. So at least for the purpose of classification, I think they are equivalent. And then these Dacre domain wall ideas, they can be turned into some topological invariants in terms of, as you surely know, the string order parameters, that kind of thing, which can be used to distinguish different states. So now, how do I actually engineer a Lindbladian to realize a particular steady state with these, features, I don't have a general or any intelligent answers to that. All I know that in some examples, for example, the example that we discussed, we can probably write down in the Bladian that does this. Yeah, beyond that, I don't have any anything general to say.
And do you know what this like? So basically, your criterion is that you have to be able to go forward and back. But do you have any idea how that constraint? Say I'm only looking at the part of the Lindbladian that goes forward, or like the part of the like. Do you have any understanding of how that constrains the allowed channels? This criterion that there should be some.
Well, here we allow we allow different quantum channels going forward and backward.
Yeah.
Right. So it could be different in the Bladians going forward and going backward. We just ask whether there exists some in the Bladian, some like finite evolution under the Bladian, for example, to connect the two states. Now, this is a bit like the adiabatic connectivity of ground states. We demand there's some unitary, some finite depth circuit that connects two things. Actually, figuring out these unitaries is not easy even for ground states.
Yeah, yeah, understood.
So right, but if we have some in the Bladian, then we can definitely use that to generate some evolution and see whether that made the connection.
Okay, thanks.
Yeah, sure. So Ruihua, I saw your hands as well. Still there?
Oh yeah. Hi, Meng. Yeah, thanks for the very nice talk. Yeah. I have a question about, maybe you comment on this, but I missed it. The density matrix has to be positive semi-definite. So when we define the channel map between two density matrix, I have to preserve that. How does that change the enter your discussion explicitly? Maybe you talk about unitary acting on Silas. Does that just automatically satisfy that? But I'm just curious how that explicitly changes the discussion.
Yeah, that's obviously. So okay, sorry, not obviously. So first of all, so the channels, preserve the semi-positive definiteness, right? That's how we define the channels. So I have to say, so from the way that the classification derived so far, we haven't, the way that we have argued it so far, we haven't explicitly used the condition of positivity. Okay. Now, there are questions you can ask. For example, one way to probably another fairly natural way to study this question is to map the density matrix into a state in a double Hilbert space, and just classify the double Hilbert space under all kinds of symmetries we have. You can ask whether these states in double Hilbert space are mapped back to reasonable density metrics. Generally, they are not, and because of the positivity constraints.
Right. Yeah.
So, but no, the way that so far we've kind of proposed the classification, I guess we haven't explicitly used it in for example, defining the Decret domain wall and all that.
I see.
Yeah.
Yeah.
Maybe implicitly somewhere, but.
Right. Yeah, that could be true. Yeah. And another probably related question is, in the case of pure state, we talk about unitary evolution and use that to build equivalence. And this is really constrained by the Lieb-Robinson bound. Do you think there exists a similar thing for a mixed state classification discussion?
Yeah, that's a great question. I would love to know whether there's something similar for there's something similar on the something like generalizes Lieb-Robinson bound. I would guess there is, but some version of it, but I don't know anything about that. Yeah.
Yeah. Okay. Yeah, thanks for the talk again.
To rigorously establish some of these things.
Yeah, thanks. Yeah.
Let's go. Any question, comments? River's down, right?
Yeah, River's, I think, I think he's done. Still has hands up. I guess that's just.
Okay. Yeah, so,
Sorry about that.
well, thank you.
Okay, thank you.